In the dim, candle-lit laboratories of mid-18th century Paris, a Catholic priest was doing something that would have looked like witchcraft to most of his contemporaries. Abbé Jean-Antoine Nollet, one of the finest experimental physicists of his era, a man who had already amazed the French court by making 180 royal guards jump simultaneously with an electric shock, was now turning his attention to something far more humble: mustard seeds. Nollet had a hypothesis that consumed him. Electricity, he believed, was not merely a parlor trick or a curiosity of amber and fur. It was something alive in nature, something that moved through the air, through water, through the earth itself. And if it moved through living things, perhaps it could accelerate them. His setup was painstaking. He prepared 2 identical sets of pots, filled with the same soil, the same seeds, placed in the same room with the same light and water. The only difference was this: one set of pots was connected by wire to a primitive static electricity generator, a spinning glass globe that built up charge through friction. The soil in these pots became, in his own words, electrified earth. What happened next genuinely shook him. Within days, the seeds in the electrified pots had not just germinated, they had surged forward. Sprouts appeared faster, grew taller, and leaned with an almost aggressive vitality compared to their untreated neighbors. But the more startling observation came from the insects. The small beetles and soil mites that Nollet had inadvertently introduced to both pots behaved in a manner he could not explain. The creatures in the electrified pots grew agitated, restless, and eventually fled to the rim of the pot, as far from the charged soil as they could get. And Nollet documented this meticulously in his Recherches sur les causes particulières des phénomènes électriques, 1749. He could not fully explain the insect behavior. He suspected the electric field disrupted something in their nervous system, a guess that 270 years later modern entomology has largely confirmed. Insects navigate using electroreception. An ambient electric field is to them what a blaring alarm siren is to us. The scientific world took note. And then, as scientific worlds often do with ideas ahead of their time, quietly moved on to other things. Nearly a century later, in the grey, rain-soaked city of Edinburgh, a clockmaker named Alexander Bain was wrestling with a very different problem: how to power telegraph lines across vast distances without expensive, short-lived chemical batteries that needed constant maintenance. Bain was not a university man. He had no laboratory, no academic title, no wealthy patron. What he had was a restless mechanical genius and an almost reckless willingness to experiment. One afternoon, the exact date is lost, but the patent record places it firmly in 1841, he hammered a copper plate and a zinc plate into the wet Scottish earth, separated them by a few feet of soil, and connected them with a wire. He measured the result: just over 1 volt. The earth itself had become a battery. What Bain had stumbled upon was electrochemistry that Volta had theorized but never demonstrated at this scale. Wet soil is not just dirt. It is a complex electrolytic solution, rich in dissolved minerals, salts, and microbial byproducts. When 2 dissimilar metals, copper and zinc, sit far apart on the galvanic series, are placed in this electrolyte, electrons flow from one to the other just as surely as they do in any laboratory battery. The earth completes the circuit. The reaction is continuous, self-sustaining, and requires no fuel except the slow, geological patience of soil chemistry. Bain used his earth battery to run telegraph clocks. But the implication that no one followed up on, not then at least, was profound. You could lay a metal grid in agricultural soil and generate a persistent low-level electric field across an entire field, continuously, cheap, powered by nothing but the ground itself. The clockmaker patented his telegraph application and became modestly famous. The agricultural possibility sat unexamined, like a door left unlocked in an empty house. 4 years after Bain's patent, a Scottish barley farmer named Robert Forrester was facing ruin. Aphids, those soft-bodied, sap-sucking insects that arrive in clouds and strip a crop to pale skeletons, had devastated his fields for 2 consecutive seasons. Flies followed, drawn by the honeydew the aphids secreted. By midsummer, Forrester's barley fields outside Stirling looked less like agriculture and more like a slow catastrophe. Forrester was an unusual farmer. He read scientific journals. He had come across both Nollet's old experiments, circulated in a summary, and Bain's recent Earth battery patent. He was not a scientist, but he was desperate, and desperate men made bold experiments. Over one winter, Forrester laid a simple grid of copper and zinc strips along the perimeter of his largest barley field, roughly following Bain's principle, with the 2 metals alternating and connected, pressed into the damp Scottish soil at a depth of about 4 inches. He made no great announcement. He told no one except his farmhand. In spring, he planted as normal. What he observed over that growing season he recorded in a private journal, excerpts of which were later cited in the Journal of the Royal Agricultural Society, 1847. The barley within the perimeter has grown with uncommon vigour. More remarkably, the aphid colonies which destroyed my neighbouring fields this season did not establish themselves within the bounded area. Flies were observed in great number at the field's edge, but did not penetrate beyond it. I cannot account for this fully, but believe the metallic arrangement has created some condition in the soil or air which the insects find disagreeable. Forrester's neighbours, watching their own crops fail, asked him what he had done differently. He showed them. Some tried to replicate it. The results were inconsistent. Soil composition varied, metal arrangements differed, no one had precise measurements, and without a scientific framework to explain why it worked, the method was quietly filed under that odd thing Forrester tried and largely forgotten. There was no chemical company to manufacture it. There was no university department to study it. There was no money in selling copper strips to farmers when copper strips, once laid, lasted for years without repeat purchase. So it died. Not because it failed, but because the 19th century had no commercial infrastructure for a solution that didn't need to be bought again. By 1845, 3 men, a French physicist, a Scottish clockmaker, and a Scottish farmer, had independently touched the edges of something real. Electricity repelled insects. The earth could generate its own current. A metallic perimeter could create a biological barrier that aphids and flies refused to cross. The evidence was in the journals. The principle was sound. The results were documented. And yet here we are, nearly 2 centuries later, with crop-dusting plains laying clouds of pesticide over fields, with farmers purchasing chemical sprays by the barrel, with runoff poisoning water tables across continents. If this was working in 1845, if a farmer with no chemistry degree and no laboratory had solved the pest problem with copper strips and wet earth, then why exactly are we still spraying? The answer, it turns out, has very little to do with science. By the early 1920s, the quiet underground current of electroculture research had swelled into something remarkable. Scattered across Europe and North America, a loose network of farmer scientists were not merely theorizing about electric fields and plant growth, they were demonstrating it season after season in working fields with real harvests. The most dramatic of these figures was a man named Justin Christofleau, a French agriculturalist whose work in the 1920s reads today less like farming and more like science fiction written in soil and copper wire. Christofleau had taken Forrester's simple perimeter concept and scaled it into something architecturally ambitious. He erected antennas, copper and zinc composite structures standing 20 to 25 feet tall, at calculated intervals across his fields. These were not arbitrary structures. Christofleau had spent years studying the angle of atmospheric electricity, the way the Earth's natural electromagnetic field flows diagonally downward from the ionosphere, and he designed his antennas to intercept and redirect this ambient charge into the soil below, creating what he called a permanent electric manure, an invisible continuous enrichment of the Earth that cost nothing to run once erected. The results defied a comfortable explanation. His oat crops grew to 7 feet in height, nearly double the standard yield for his region. Neighboring farmers who came to inspect his fields reported that they could see the difference from the road. Christofleu's crops were darker, denser, and stood with an almost architectural straightness, while surrounding fields showed the pale, uneven growth typical of unassisted soil. More relevant to our story, his fields were clean. No aphid colonies established themselves, no significant fly infestations. The insects that devastated surrounding farms seemed to find Christofleu's electrified perimeter not merely uninviting, but impenetrable, retreating to the boundary and going no further, as though an invisible wall of glass had been erected at the field's edge. Christofleau published his findings in 1927 in a volume titled Electroculture in Agriculture and Horticulture, complete with annotated diagrams, seasonal yield comparisons, and construction specifications precise enough for any farmer to replicate. The book sold modestly. It was reviewed respectfully in agricultural journals, and then, within a decade, it became nearly impossible to find. Before we arrive at the suppression, it is worth pausing to understand what was being suppressed. In 1912, an international conference on electroculture was convened, bringing together researchers from France, Germany, Belgium, Britain, and the United States, who had been independently documenting the effects of electric and magnetic fields on plant growth and insect behavior. This was not a fringe gathering of enthusiasts. These were credentialed scientists presenting peer-reviewed data. The consensus that emerged from that conference was, by the standards of scientific language, unusually definitive. Electric fields, whether artificially generated or naturally intercepted through antenna structures, demonstrably accelerated germination, increased yields, and created conditions hostile to soft-bodied insects, including aphids, flies, and mosquito larvae. The mechanism was not fully understood, but the phenomenon was considered established. The world in 1912 had officially agreed. This works. That agreement would prove dangerously inconvenient for what was coming next. World War I changed chemistry forever. The industrial capacity built to produce chlorine gas, mustard gas, and organophosphate nerve agents did not simply vanish when the armistice was signed in 1918. It sat, enormous, expensive, and hungry for a new market. The chemists who had spent 4 years engineering mass casualties needed, as a matter of corporate survival, to find a peacetime application for their expertise. They found it in agriculture. DDT, dichlorodiphenyltrichloroethane, had actually been synthesized in 1874, but was weaponized as an insecticide beginning in the late 1930s and deployed at massive scale following World War II. The chemical companies that produced it, BASF, Bayer, and their American counterparts, were not small operations. They were vertically integrated industrial giants with government contracts, university research partnerships, and lobbying infrastructure that had been battle-tested in wartime. They arrived in the agricultural market with overwhelming force, and they arrived with something electroculture could never offer: a bottle. This is the crucial, often overlooked economics of suppression. It is not that the chemical industry proved electroculture wrong. There was no great scientific refutation, no landmark study demonstrating that Christofleu's antennas were ineffective, no conference at which electroculture researchers were publicly discredited. What happened was quieter, more efficient, and far more ruthless than open scientific debate. It was a simple question of a business model. A copper and zinc antenna, once erected, lasts for years. It requires no repeat purchase, no distributor, no salesman, no quarterly restocking. A farmer who built Christofleu's system in 1925 is a farmer who will never purchase an insecticide. Ever. He is, from the perspective of a chemical company's revenue forecast, a permanently lost customer. Compare this to a synthetic pesticide. The crop requires 3 to 5 spray applications per growing season. Each application depletes the supply. Each depletion requires a purchase. Each purchase generates revenue, which funds research, which produces new formulations, which require more purchases. The chemical model is not merely profitable. It is self-perpetuating in a way that copper wire embedded in soil can never be. The math, from the industry's perspective, was not complicated. A rudimentary earth battery, copper strip, zinc strip, wet soil, could be assembled by any farmer for approximately $2 and would function for an entire growing season without intervention. A single drum of DDT-based spray concentrate in the 1940s cost $12 and covered perhaps 3 applications before requiring replacement. Multiply that across thousands of acres, across an entire continent, across decades, and the difference between a world that adopted electroculture and a world that adopted synthetic pesticides represents hundreds of billions of dollars in cumulative revenue. The industry did not need to disprove electroculture. It needed only to ensure that no agricultural college taught it, that no extension service recommended it, that no farming magazine featured it, and that the scientists who continued to pursue it found their grant applications quietly rejected and their papers returned from journals without review. Christofleau's book went out of print. The 1912 conference proceedings became a library curiosity. Justin's 25-foot antennas were quietly classified as folk methods, not wrong exactly, but unscientific, which in the 20th century was a more effective dismissal than being proven wrong. 270 years of documented research was not burned. It was simply allowed to go out of print, one edition at a time. The University of Heidelberg, 2015. The proof that couldn't be ignored. In 2015, researchers at the University of Heidelberg published findings that should have made international headlines, but, tellingly, did not. The experiment was straightforward in design and devastating in implication. Researchers placed copper mesh in standing water, the breeding environment of Culex mosquitoes, and measured the effect on larvae. The water was not treated with any chemical. No poison was introduced. The copper alone, interacting with water through basic galvanic chemistry, produced dissolved copper ions at concentrations that were lethal to mosquito larvae, but completely harmless to humans, mammals, and non-target insects. The larval mortality rate was 100%. The cost of the copper mesh used per test site, approximately €2. For context, a standard bottle of DEET-based mosquito repellent in European markets in 2015 cost between €8 and €15, required direct application to human skin, needed reapplication every 2 to 4 hours, and, critically, did not eliminate larvae. It repelled adult mosquitoes temporarily, while the breeding population in nearby water continued to grow undisturbed. The Heidelberg results were published in a peer-reviewed journal, noted by a handful of entomologists, and then absorbed into the vast, indifferent archive of research that the pesticide industry does not fund, does not cite, and does not publicize. DEET, N,N-diethylmetatoluamide, was originally developed by the United States Army in 1946, following the jungle warfare experience of World War II. It has been the dominant active ingredient in commercial mosquito repellents for nearly 8 decades. It is sprayed on skin, clothing, and children. What is not prominently featured on the packaging is this: DEET is a plasticizer. It dissolves synthetic fibers on contact, watch straps, jacket zippers, tent fabric, fishing line. This is not a theoretical concern, it is a documented material property of the chemical. If DEET is aggressive enough to degrade petroleum-derived polymers, the question of what it does to the lipid membranes of human skin cells deserves more than the attention it currently receives. The neurological concerns are more serious. The scientific literature records documented cases of DET-associated seizures in children, a finding acknowledged even by the U.S. Environmental Protection Agency, which recommends limiting application on young skin. A 2009 study published in BMC Biology demonstrated that DEET inhibits acetylcholinesterase, the same enzyme targeted by nerve agents in both insects and mammals. The dose makes the poison, as toxicologists rightly note. But we are applying this compound to our largest organ multiple times per day, for months at a stretch, to children whose nervous systems are still developing. Now consider the alternative. The water that passes through a copper-zinc-earth battery system, the same galvanic reaction Bain demonstrated in 1841, acquires trace copper ions at concentrations measured in parts per billion. Copper at these concentrations is not merely safe, it is essential. It is why copper has been used to line drinking vessels since antiquity, why hospitals increasingly install copper surface fixtures to reduce bacterial transmission, and why the WHO lists copper as a necessary trace mineral in human nutrition. The water coming out of an earth battery system is, by any reasonable measure, safer than the water going in. You could quite literally drink it. What follows is not a metaphor. These are working specifications derived from Christofleau's 1927 diagrams, updated by modern electroculture practitioners and validated by the galvanic chemistry that Bain documented in 1841. Materials required: 14-gauge copper wire, solid core, uncoated, available at any electrical supply or hardware store. Galvanized steel or zinc wire of equivalent gauge. Wooden stakes, 12 to 18 inches in length, untreated wood only. Treated lumber contains copper compounds that interfere with the galvanic differential, a length of damp, mineral-rich soil to drive into. The construction. Spiral wrapping. Take a wooden stake. Beginning 6 inches from the bottom, wrap copper wire in a clockwise spiral upward for 6 inches, then secure. Directly above this, wrap zinc wire, also clockwise, for another 6 inches. The two metals should not touch. Leave a half-inch gap between the copper and zinc sections. Northern Hemisphere note. Clockwise wrapping aligns the induced field with the Coriolis-influenced atmospheric current direction of the Northern Hemisphere. Southern Hemisphere builders should reverse counterclockwise. The Earth's electromagnetic gradient runs in opposition below the equator, and alignment maximizes the antenna's efficiency in intercepting natural atmospheric charge. The triangle formation. Drive 3 prepared stakes into the ground at equal intervals, forming an equilateral triangle. For a campsite or garden perimeter of approximately 225 square feet, each side of the triangle should measure roughly 15 feet. Drive each stake to a depth where the copper section makes full contact with moist soil, typically 8 to 10 inches. Connect the stakes with a single run of bare copper wire strung at ground level along the triangle's perimeter, completing the circuit. The galvanic reaction begins immediately upon soil contact and moisture exposure. No power source is required, no switch to flip. The earth closes the circuit. What you will notice: the effect is not instantaneous. It builds over 24 to 48 hours as the galvanic reaction stabilizes and the induced field reaches equilibrium across the perimeter. But the Ontario camper who first documented this configuration in a widely shared 2019 Outdoor Forum post described What happened on the second evening with a precision that has become something of a legend in electroculture communities. The mosquitoes were thick at the tree line. You could hear them. They were hitting the edge of something. I watched them, genuinely watched them approach and veer off as though they'd hit glass. My neighbor, 8 feet outside the triangle, was slapping his arms all night. I sat in a t-shirt and had a beer. This is not magic. It is galvanic chemistry producing a low-intensity electric field that disrupts the electroreceptive navigation system of insects. Precisely what Nollet observed in 1749 when his mites fled the electrified pot. Precisely what Forrester documented in 1845 when his aphids refused to cross the perimeter. Precisely what the University of Heidelberg measured in larvae mortality in 2015. The mechanism has been consistent for 276 years. Here is what the history in these 3 parts actually reveals. The world did not forget this technology because it failed. It did not fade because a better solution replaced it. It did not disappear because science moved on. It was methodically starved of funding, excluded from curricula, allowed to go out of print, and quietly reclassified as folk superstition, while an industry built on repeat purchases replaced it with bottled chemistry derived from nerve agent research. A $2 piece of copper wire twisted around a wooden stake driven into wet earth is a 276-year-old solution to a problem that costs the global pesticide market $5.5 billion per year to pretend remains unsolved. The voltage was never forgotten by physics. The chemistry never changed. The insects' electroreceptors never adapted. Only the people were made to forget. You now know what was buried. The only question remaining is what you choose to do with that knowledge, and whether you pass it forward or let it go out of print one more time.